Good day, everyone. In this video, we will be covering about Bernoulli equations. Specifically, we're going over concepts about conservation of mass and energy, mechanical and energy efficiency, before going to Bernoulli's equations, definition, form, and limitations. We'll be going over concepts first, followed by sample problems on a separate recording. So conservation laws first. So let's do a concept recap muna. So conservation laws, according to Sangil, are first applied to a fixed quantity of matter called a closed system, or just a system, and then are extended to regions in space called control volumes. So if you are familiar with systems and control volumes, and they're kind of familiar, which is kind of related to our previous lecture on fluid kinematics, on conversions of system analysis to control volume analysis. We'll be doing that a lot here, especially for under Bernoulli's equation. The conservation relations are also called balance equations, since any conserved quantity must balance during a process, which is the whole concept of conservation of laws. The same is true when you're talking about conservation of mass, momentum principle, and energy. Conservation laws are fundamentally a principles in physics which describes the preservation of certain quantities in isolated systems. In a nutshell, these laws state that certain properties and quantities of a system remain constant over time under specific conditions. So for conservation of mass, as you can see here, mass in is equals to mass out, or mass flow rate in, basically mass out in a controlled volume state. Here, hence there's this equation here, the rate of change of mass within a controlled boundary is for systems that are not that are compressible, but we won't be talking about compressible systems for now, but we'll be focusing on incompressible lang. Essentially, the total mass is neither created, the mass is neither created nor destroyed, it only changes form. And the total mass in an isolated system remains constant unless there's a mass input or output changes, okay? So for conservation of energy, the usual goes, energy can neither be created or destroyed. It can only change from one form to another. And for Sengel, energy can only be transferred to or from closed system by heat or work. And the conservation of energy requires that that energy transferred to or from a system during a process be equal to the change in energy content of the system. So energy in and energy out. For conservation of linear momentum or conservation of momentum principle, in a nutshell, the total linear momentum of an isolated system remains constant unless an external force is acting upon it. And our basis here is Newton's second law, which states that the acceleration of a body is proportional to the net force acting on it and is inversely proportional to its mass. The change in momentum body is equal to the net force acting on the body. So there should be a space there. So the combined mass and velocity of objects in a closed system remains constant unless there are external forces. This is something that you've learned way back in statics and rigid bodies, or statics, mechanics, and under dynamics naman. So these laws are foundations in physics, not just in and in this case fluid mechanics, and have a wide range of application across different branches of science and engineering. In our particular use case will be applications under fluid mechanics. Okay, and the understanding of how fluid behave and knowing their states are from one point to another. We will be using these laws and principles to establish what conservation laws would describe as balance equations. And from these equations, we can identify variables that we are ought to search for. Next slide. So the conservation of mass in a nutshell, just like this, is again a fundamental state in physics. And in a simpler terms, the total mass of a closed system remains constant over time, whether it be a chemical reaction or as simple as you making coffee. So I have here a sample. I use the English conversion from tablespoons to grams, a cup to grams. So essentially, when you add 2 tablespoons and 1 cup of water, approximately that's 28 grams of coffee grounds and 237 grams of already boiled water. You get 1 cup of coffee, which is roughly 266 grams, plus minus losses for evaporated water losses. The same way when you're trying to react 2 kilograms of hydrogen and 16 kilograms of oxygen, where you will get a chemical combination of 18 kilograms of water. So for closed systems, the conservation of mass principle is implicitly used by requiring that the mass of the system remain constant during a process. Again, take note of the closed system. So we're basically taking a snapshot of a particular system, and then we analyze the properties of mass, its volume, its density there. And normally they remain constant all throughout because um, they are within within the system. Now, for control volume, mass can cross the boundaries. And so here we keep track of the amount of mass entering and then leaving. And the same way with mass, we want to know if what's the state if the inlet is a lot smaller or the alpha is a lot bigger, and vice versa. What will be its velocity inlet? What would be its velocity outlet? Is there a change in properties in between? So that's what we're looking for here. So to expand it further, let's build some math into it. Okay, back in your thermodynamics days, you hopefully you recall that the mass flow rate is simply the product of its density and volume flow rate, or mass flow rate is simply the quotient of volume flow rate over its specific volume. So here density is the density of the fluid, the volume flow rate here is simply the velocity times the area of a particular cross-section. Yeah. Normally represented by this, no need for the bar, and that's fine. I usually represent this with just a V and then the dot on top. And then mass flow rate is represented here with a dot on hat. With a dot on top of its symbol. Okay? Essentially, mass flow rate is the amount of mass flowing through a cross-section per unit time. And the volume of fluid flowing through a cross-section per unit time is called the volume flow rate, this one. And volume flow rate is simply the product of its velocity in a particular cross-section and its particular cross-sectional area. Okay? So if it's most of the cross-sectional area here we'll be dealing is pipes. So it's uniformly circular. And there's a rare cases where the area would be a tube, a square one. So the conservation of mass here at control volume, this just shows the continuity equation, where again the conservation of mass, wherein mass is neither created or destroyed, just transformed from one form to another. Where in this case at steady flow control volume, your mass flow rate in should be your mass flow rate out. And this is the continuity equation, which is the relation written for differential control volume. And this will be one of your guides as well here. The same is also true for volume flow rate. So for steady flow and steady flow single stream, we have here the summation of all mass flow rate coming in equals to some mass flow rate coming out. And this is very crucial because sometimes your outlet could be 2, 3, or more. And your inlet could be the same thing as well. So hence you just sum all the same thing to have your total mass flow rate. In a single stream steady flow equation, we have mass flow rate in 1 going and mass flow rate out 2, which could translate in this particular equation where mass flow rate is equal to density times velocity times area. And velocity and area is also your volume flow rate. So the same equation that we had here, density times volume flow rate. Mass flow rate is also equal to density. If you gotta break it down further, density times velocity times area. At least in this particular case, we'll call it the inlet, the point 1. It should be equal to the property here in exit at this, which is mass flow rate number 2, subtube, which is density times velocity times area 2. So fluid density, fluid velocity, and I just wrong spelling. It's area of inlet or outlet. Yeah, let me correct that for you ASAP. There we go. There we go. Area of inlet or outlet, and then its corresponding units. Again, when you're writing equations, you need to be careful and always do unit analysis so that you arrive with the proper unit and cancel the ones that you don't need. So for steady incompressible flow, volume flow rate in equals volume flow rate out. Technically, they're one and the same. And you can also express volume flow rate as velocity times area. So this is the fluid velocity, and then the area of its particular inlet or outlet. Sometimes on other books, flow rate, volume flow rate is written as Q1 or Q2, but you normally use Q in terms of heat. So in this particular nomenclature, we're gonna be using your volume flow rate as your V equals to a V with a dot on top of it. Okay. We'll have sample problems in a separate recording after this. You may review your concepts here on chapters 4 for Bernoulli Equation, and there's a lot of sample problems that you can go over there and have a practice, have a go with the sample problems there and apply the concepts. But I will be following up with a separate recording on that. So now we're gonna go with mechanical energy and efficiency. So mechanical energy is defined as the form of energy that can be devoted to mechanical work completely and directly by an ideal mechanical device, such as an ideal turbine, or in this case, we have pumps. So here I have a sample of pumps dito. And just take note, these are 3D models, are not scale or accurate, but only serve as a model. And many fluid systems are designed to transport a fluid from one location to another. So in the case of a dam, so we convert from a higher place to a lower, and it goes through a turbine and it generates electricity there. In the case of a pump, you transfer from one fluid to another, either from a lower elevation to a higher elevation, and that one consumes electrical input and converts that to mechanical output, so that you can transfer a bunch of fluids there, whether that's going to be gas uh, or, 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 or liquid. Here, kinetic and potential energies are the familiar forms of mechanical energy. Okay, and thermal energy is not mechanical energy, however, and then since it cannot be converted to work directly and completely as dictated by the second law of thermodynamics. So here we dictate the genetic equation for mechanical energy as, and also the basis later on for our Bernoulli equation. That this one mechanical energy is this is mechanical energy on a per unit mass basis. So this is kilojoules per kilogram, and then this chart here, in this sector here, this pressure over density is your flow energy. This is your kinetic energy, V squared over 2. And this is your potential energy. This is acceleration due to gravity, times elevation, Z, sometimes represented as H. The change in mechanical energy is just a matter of representing the change in mechanical energy at two different points in the equation. So at one could be at a higher elevation to a lower elevation or vice versa. So in this here, this is the spread out equation right here. In this case, let me just do a little bit of edit here. Okay. There we go. So again, let me just go back here. So again, just a recap. So we're jumping now from conservation of mass principles, and now we're gonna apply it on mechanical energy and efficiency. Okay. And this is the equation for the mechanical energy, and later on will be expanded further on our Bernoulli's equation. Okay. So the ending unit for mechanical energy will be kilojoules per kilogram basis here. Okay, this is basically an energy form on a per unit mass basis. This equation here again is a representation of two different points and understanding the change in mechanical energy. So yeah, this is mechanical energy per unit mass basis and mechanical energy change at incompressible flow. So we have two samples here. We have a turbine and a pump, a centrifugal pump to be honest. And again, these are 3D models and these are not to scale but or accurate, but only serve as a model. Okay. So for turbine, we're gonna be dealing with a lot of equations here, but let's start with the basic. So with turbine, you are getting mechanical power decrease of a fluid. So that could be gas, that could be usually water in this case. And then that one converts it into a mechanical power output. And you will get the efficiency of the turbine there, where it's just simply the mechanical power output over the mechanical power decrease of the fluid, or input in this case, which also translates as the work is shaft out, and the the change in mechanical energy of the fluid. In this case, work of turbine divided by work of turbine E, energy, mechanical energy input. And then from here, your mechanical power input going now to the generator, so it will become your mechanical power input. From your mechanical power output, it will now become a mechanical power input, where it generates electricity. So in this case, the efficiency of the generator, you can get that by getting the quotient of electrical power output over mechanical power input. So work electricity out divided by shaft in. These are unitless, by the way, since we're talking about efficiency. And normally your ending unit here are in percentage. And to get the overall efficiency of your turbine to generator, you simply multiply the product of two efficiencies of the turbine and generator so that you can get the overall efficiency of as a whole. So in this case, you're going to get the input here, the change in mechanical energy input, and then your numerator will be your electrical output, and you will get the efficiency of turbine and generator. For turbine, it generates its power generating machine system. For pumps, it's power consuming, because it's the reverse. Here, we need to have electrical input so that you can have mechanical output. So there we go. So here we're talking about the motor. It's a two difference. This one's a generator, which is a power generating device, and we have here a motor, which is a power consuming device. And in this case, the input here will be your electrical, and then your output will be mechanical. And to get the efficiency of the motor, mechanical power output divided by electrical power input will get you the efficiency. So that's the work of the shaft out and work of the electrical in. And then from here, your mechanical power output now towards the pump, this is the centrifugal pump now, will now be your input. Here, the mechanical power, the efficiency of the pump will now be the mechanical power increase of the fluid, change in energy of mechanical fluid, divided by its mechanical power inputs, or the work and shaft. That in turn turns the pump and produces the mechanical power increase of the fluid here, or at least the transfer of fluid. And to get the overall efficiency of the pump motor, you simply multiply the efficiency of the pump and motor to get the whole efficiency as the system. We will have more sample problems in a separate recording. Now with the Bernoulli equation. So the Bernoulli equation essentially is the approximate relation between pressure, velocity, and elevation, and is valid in regions of steady, incompressible flow where net frictional losses are negligible. So these are very important because that is the requirement or the condition in which Bernoulli equation is applied, and we'll be discussing more about its limitations later down the slide. We have two proponents here, mainly Sir Daniel Bernoulli, and stated in words by the Swiss mathematician in a text written in St. Petersburg, Russia, in 1738, and of course expanded further by Leonhard Euler, his associate. So the Bernoulli equation is a fundamental principle in fluid dynamics, which again relates pressure, velocity, and and gravitational potential energy, in this case elevation. And it's a statement of conservation of energy for an inviscid, incompressible fluid flowing along a streamline. Here's a quick derivation of it, and again, it's viewed as the conservation of mechanical energy, which started with force equals to so summation of all the forces equals the mass times acceleration. And you imagine a particular point in a streamline, and you expand this formula, and this is using our general mechanics and applying the equations here, you will get this one, or in much more general term, this one. Essentially, this is the Bernoulli equation in its energy form, as you heard it earlier, or what we call mechanical energy earlier. So again, Bernoulli equation is the sum of the kinetic potential energies of a fluid particle and is constant along a streamline during steady flow when compressibility and frictional effects are negligible. So this is the general formula. A steady flow along a string, it is simply the sums of all the change in pressure per density plus the velocity, change in velocity per unit time, plus acceleration due to gravity and change in elevation, basically. Or in a much simpler form, the energy form is simply the pressure divided by, this is the flow energy, this is the pressure divided by density, this is the flow energy. V squared over 2 is the kinetic energy, and this is the potential energy, and it's constant. When you're trying to determine, when you're trying to determine two separate, the variables at two separate, or the conditions at two separate points, you represented them as such. One way or another, if it's the same elevation, your potential energy is gone because there's no potential energy when there's no elevation. If it's the same streamline, when there's elevation, usually there will be a change in velocity, and when there's an increase in velocity, there will be a decrease in pressure, and you would know that when you're trying to solve some problems. The other forms of Bernoulli equation are as follows. So this is as in incompressible steady flow, so that's one of the conditions. So we have the pressure form and the head form. So for pressure form, we simply multiply everyone by its density, and we have this. This here is the static pressure. This here is dynamic pressure, and this one is something you all familiar with during our hydrostatic forces. This is the hydrostatic pressure, where this is equals to density times acceleration due to gravity times elevation. Dynamic pressure is simply the quotient, and this is simply the product of density times velocity squared over 2, and then this is static pressure. In head form, we normally express, in engineering, we normally express Bernoulli equation. We can express pressure also in terms of height, and it's very applicable, especially during pump selection, which I'll discuss more later. So here, we divide everyone by acceleration due to gravity and in density. So there will be pressure divided by acceleration due to gravity times density plus p squared over 2g plus z. And this is to get the total head form, and this is constant at incompressible steady flow along a streamline. Another equation which you can derive from the Bernoulli equation is Torricelli's equation, which relates the speed of fluid flowing out of an orifice to the height of a fluid above the opening, which is simply the velocity equals to square root of 2 times the square root of the product of 2 and acceleration due to gravity and elevation. This one you don't have to memorize because you can actually derive it from here. And we will have another sample problem for this so that you know the breakdown for this. Okay. Other concept for Bernoulli equation is we're going to talk about the total pressure. So we're going to talk Bernoulli equation in pressure form, where the sum of the static, dynamic, and hydrostatic pressures is called the total pressure. So obviously the ending unit here will be kilopascals in SI and sometimes PSI or English. We call that the stagnation pressure, the sum of the static and dynamic pressure. The static and dynamic pressure is called the stagnation pressure. And the stagnation pressure represents the pressure at the point where the fluid is brought to a complete stop isentropically. And to calculate its velocity, you simply rearrange this equation, and then you will have this in meters per second. A clear example of this, if you watch the video, is the static tube. You can know more about this here about the parts, or you can simply watch the video I recommended a few weeks ago. Next up is the total head, or we're going to talk about the hydraulic grade line and energy grade line. So here we're expressing Bernoulli equation in head form. Essentially, the total head is the sum of the pressure, velocity, and elevation heads along a streamline is constant, which during steady flow, when compressibility and frictional effects are negligible. The solid line here is your energy grade line. The broken line here is your hydraulic grade line. So simply, the Bernoulli equation in head form is expressed as such, where the pressure head, that is pressure divided by the product of acceleration due to gravity and density. This is the velocity head, v squared over 2 twice the acceleration due to gravity, and then elevation head. Then eventually, this is the h, which is our variable for total head. The hydraulic grade line is the line that represents the sum of the static pressure and the elevation heads. So that's simply this and the elevation here. The energy grade line, the line that represents the total head. So essentially here, the whole thing. The difference between the energy grade line and the hydraulic grade line is simply the velocity head, or dynamic velocity, which is v squared over 2g. So you might ask, sir, why do we need to represent it as head? Well, for one, it is convenient to represent the level of mechanical energy graphically using heights to facilitate visualization. So that you can actually determine the amount of pump requirements that you need, and facilitate visualization for the various terms of the Bernoulli equation. Head is also used as one of the major parameters in pump selection. In idealized Bernoulli type flow, EGL, or energy grade line, is horizontal, and its height remain constant. But this is not the case for HGL when the flow velocity varies along the flow. And normally, when the pressure is 0, it will intersect. Hydraulic grade line will intersect at that. So at the outlet, you would see that the hydraulic grade line would go where pressure is 0. As beautiful the Bernoulli equation is, there are certain limitations that you must consider. For one, in general, frictional effects are negligible, and with large cross-section, especially at low flow velocities. Frictional effects are usually significant in long and narrow passages, and in the wake regions downstream of an object, and in diverging flow sections as diffusers because of the increased possibility of fluid separating from the walls in such geometries. Okay. Frictional effects are also significant near solid surfaces, and thus the Bernoulli equation is usually applicable along a streamline, steady flow, and the core region of the flow, but not along a streamline close to the surface. So it's not gonna be here, but somewhere in the middle. Okay. Bernoulli equation is applicable to steady flow, and Bernoulli equation has no shaft work when they're not considering them. The fluid, it must be an incompressible flow. So we're here talking with you cannot compress it assumes the fluids as incompressible. We neglect heat transfer here and must flow along a streamline. Any disruption the streamline Bernoulli equations is not applicable anymore, or rather the math won't work basically. So I have here the summary of the formulas that you could use, and now you may start answering some of the sample problems there just to figure it out. I will follow this up with a separate video, and you can find this in the book on the reference below. Thank you so much.